Dear all, welcome to the class on number systems. In this particular video lecture, we will try to understand what are the number systems, why they do require, and then finally we will try to find out what are the different techniques and methods for converting one number system to the another number system. So let us start with the what are the contents we are going to cover in this particular video lecture. First, we will try to understand the motivation behind the topic of today's concern. Then we will having a bit of discussion about the learning objectives out of the today's video lecture, and then we will move on to the different number system types available, and then finally we will try to find out the methods and the techniques which are used for converting one number system to the another. So let us start with the motivation. Dear friends, as we know that everything motivation for everything motivation is a very important task. So we all know that we are using the numbers to perform several tasks in our daily lives for many years. In fact, I would like to say for many centuries. What the numbers can do and what they are doing for so long time for us. So they are doing communication for us. They are used to perform the different kind of tasks. It may be some computational, some mathematical, some logical, or some other task. Means the different n number of tasks they are doing for us for many years. They are being used to quantify the things. They are also being used to measure the things or to measure the quantity. And finally, if I say that numbers have become symbols of the present era. So dear friends, now with this slide you can understand the motivation behind the number system, which is the today's topic of concern. Now we move on to the next slide, which is also a very important thing, that what are the learning objective out of this video lecture. So as I'm telling you that number systems, so they are different type, means that we will be able to understand the what are the decimal number system, what are the binary, what are the octal, and what are the hexadecimal number system. Then in the second learning objective, we will be able to explain how a number with one radix or one base is converted into a number with another radix or another base. And then finally, we will be able to summarize the different advantages of using the number systems. Now we move on to the next, number system types. So now this very good picture is coming in front of you that shows the different types of number system. As we discussed in the previous slide, that there are many number systems ranging from decimal, which is the oldest system basically, which is based on the Indian numeral system, and then binary, then octal, and then hexadecimal. You know, decimal, we have been using it for many years or many centuries, and it is based on the Indian numeral systems. And now this particular method have been popularly used in society for many different things, what we discussed just a couple of slides earlier, to count the things, to measure the things, to quantify the things, and even to communicate. That is the strength of this number system. And now the radix or base, it is 10. Why it is 10? Because this particular number system is having 10 digits, which range from the 0 to 9. And dear all, with the advent of the technology, electronics and computer technology, you know that electronic circuit, they do work on the principle of on and off state. Means the by state, the on and off two state, which is in the terminology of a computer, it is called the 0 and 1. That is why the binary is there. So binary numbers are the product of, they are the invention when the this digital logic circuit came into the picture. Because you, as I'm telling you, the digital logic circuit that do work on the principle of by state, that is the on state and the off state. On state, off state, they are represented in numbers through 0 and 1. Generally we do represent, generally computer sciences and the designers do represent 0 as off and 1 as on. Some exceptions may be there depending upon the requirement. Then the binary system, it is called because it is having the two base or radix, and 2 is what representing because it have the two digits 0 to 1. And then you know that octal and hexadecimal other number systems are also being popularly used in number system. And now the very important questions arises here, that when we have the binary already in place, then what is the requirement of these octal number systems and these hexadecimal system. So now, dear friend, the question is very obvious, because octal number systems and hexadecimal number systems, they are, you can say, they came into the picture after the binary. The thing is that the reason for their existence of the octal and hexadecimal system is that if we represent anything means it is a quantity or some other thing, or some miserable things, or some any other thing. If we represent it through the binary, then we know that in binary there are only two digits, 0 and 1. So then using the binary state binary system, many times representing a long things require large number of digits to represent, and many times it is very difficult to handle, and especially when you are going to compute the number, because ultimately your cpu within the system, it is all about to compute the arithmetical logic operation. And when you are performing the arithmetical logic operation on a very long list of, or very long string of the 0 and 1, then it is very difficult to handle during the computation, as well as the storage also becomes very difficult. So octal and hexadecimal, you can think of, they are the byproduct of these binary numbers. They can be used in situations where using the binary numbers require large number of digits to represent a number or anything. Then octal and hexadecimal number system in these particular scenarios are very handy and very useful. Now let us have a look on the octal number system. As the name suggests, the base for this particular number system is 8, and the 8 is why, because the number of digits are 0 to 7, 0 to 7. These are 8 digits, and that is why it makes the octal number system base 8. Now the hexadecimal number system, which is another advancement, you can say the advancement of the octal number system, it does have the base or radix 16. It means it is having 16 digits ranging from 0 ranging from the 0 to ranging from 0 to 15. But now make sure that 0 to 9, they are represented as it is, but from 10 to 15 they are representing through A to F. Means 10 is A, 11 B, 12 C, 13 D, 14 E, and then finally 15 F. This is the representation convention in the case of hexadecimal number system. Now, after understanding the different types of number system, I just want to conclude this particular table, which is available on the screen, that decimal number system, it was the earliest method of representing the number and very popularly still used nowadays. But you know, binary system came into the picture, came into the world after the advancement of the electronics and computer technology. As we know that computer works on the fundamental of 0 and 1, means the on and off, the electronics and computer, they go hand in hand. So that is why the binary numbers came into the picture. And then finally it is the octal number system and hexadecimal number system, which are very handy and very useful in this scenario where representing a large quantity or large number through binary is difficult. So in those scenario, octal and hexadecimal can play a role. And now we move on to the slide next, which is the number system conversion. Now this is the very good picture coming on the screen. If we talk about the number system conversion, which is a very important topic of the digital electronics, and very important topic, one has to understand, and being a student of the computer and IT branch, we have to understand how these number system works, how they can be converted from one form to the another, what are the advantages and disadvantages of using the one number system as compared to the another number system. So now when we are talking about the number system conversion, so we would be able, we must be capable from converting any number system to the any other number system which exists in the world. As you can see this picture, we will be able to, after just completion of this particular video lecture, we would be able to uh, complete, and we will be able to do the number conversion from decimal to binary, from decimal to hexa, from decimal to octal. Similarly, from binary to octal, binary to decimal, binary to hexa, means we would be able to convert a number system in one form to the any other form which does exist. So this is the meaning of the number system conversion. And now we move on to the next slide. It is the continuation of the previous slide. In general, conversion between numbers with different radices, you can remember radices is also called the base, as the radices for the decimal system is 10, because there are 10 digits 0 to 9. So what I mean to say here, radices, in general, conversion between numbers with different radices cannot be done by simple substitution. It is not like that okay, you can substitute one digit to another and you will be having the equivalent result in the another system of the one system. You require such conversions would involve the arithmetic operation. They do require certain kind of arithmetic when you want to convert a number from the one system to the another. Now let us work out procedures for converting a number from one radix to the another radix and vice versa. Now continuation to the last example, which was the conversion from decimal number system to binary system, but it was, so last example was the conversion of decimal number to the binary number, but that was a integer number. Now we will try to understand the conversion from decimal number to the binary number with a fractional part. So this particular process is bit different from the previous one. So in the last example where we converted the integer decimal into the binary, but here we are trying to convert the fractional integer into the binary. So the process is absolutely different. So here, rather than using the division operation, we will use the multiplication operation. In this particular example, we will take first the given number 0.8125 and we will multiply it with the 2 rather than divided by 2, as we did in the last example. Then now we can find out the multiplication, which is 1.6250, and now we can take the integer part. We can now take the integer part of this particular uh, computation of this particular multiplication, which is the 1 here. Now we will write 1 here, and now we move down to the iteration. Now we will take the fractional part. Fractional part is 0.6250, 0.625, which is again multiplied by 2. Now the multiplication is 1.250, and now we will again take out the integer part out of this multiplication, which is 1 here. Now we move down to the table. Now we will take the fractional part, which is the 0.250. Now 0.25 is gets multiplied by 2 again, and the result is 0.50. Now we will take the integer part of this multiplication, which is the 0. We will write 0 here, resultant integer part. It is called the resultant integer part. And now moving down to the table, now we will take the fractional part out of this multiplication, which is the 0.5. Now it is gets multiplied by 2 again, and the multiplication is 1.0. So again we will take the integer part out of from here, and it is the 1 here. And now we move down to the table. So it is 0.0. 0.0 is 0. It's get multiplied by 2, and the final result is 0. So now we will write out the integer part of 0. This computation means it is the 0. So now, dear friends, we are almost ready with our desired result. Now again remember, we will write all these resultant integer part into the top to bottom order. Just reverse what we did in the previous example. as I am again repeating, previous example was the conversion of decimal number to the binary, but with the integer part. But here decimal to binary conversion for the fractional part, so we have computed the resultant integer part here with the help of this multiplication operations. So now we will write all these numbers in the top to bottom order. So it is 1 1 0 1 0. So friends, we are ready with our desired result. So it is coming, it is showing on your slide that this will be 1 1 0 1 0 1 1 0 1 0. Obviously it is preceded with the point because it is a fractional number. So 0.11010 in binary is equivalent to the 0.8125 in the decimal number system. Now we move on to the next slide, which is showing the example of how we can convert the number in a decimal system to the number in an octal system. Now friends, again we will try to understand this conversion with the help of a very good example. It is the 678 on base 10, and we want this particular number to be converted into the base 8. So again, as I told you that when we were converting the number from decimal to binary, so we were dividing the source number by the 2, but here because we are trying to convert decimal to octal, which is a base 8, so now we will divide the 678 with the 8 because the desired system's base or radix is 8. So first we will divide the 678 with 8. So we get here 84 as a quotient and 6 as a remainder. Now again 84, we will replace 84 in place of 678, and again we will divide the 84 with the value 8, and now we get the 10 as quotient and 4 as the remainder. Now again we substitute the 10 in place of 84, and now we divide the 10 with the 8, and now we get the quotient as 1 and the remainder as 2. Now again repeating and continuing the same iterations, now we substitute 10 with the value 1 what we computed in the previous iteration as a quotient. So 1 here it is replacing the 10, and now 1 is divided by the 8, and now we get the result 0 as the quotient and remainder as 1. Now friends, as I told you, when we were trying to convert decimal to binary, that all these computed values uh, for the remainder, now we will write these values in the bottom up order, from starting from here and going upward up to here. So we will write 1 here from left, then 2 moving to the right, then 4, and then 6. So this is our desired result. This is our, what is the value of the 678 in base 10. It is in base 8, 1 2 4 6. Now moving further, now how we can convert the decimal number to the hexadecimal. Now the procedure is same. Dear student, up to this moment we have understood how we can convert decimal to binary and decimal to octal. Now the same procedure will be applied for converting decimal number to the hexadecimal. It is again 678, the same number what we took in the previous slide, but here our desired base system is 16, which is the hexadecimal. This 16 is also represented with the capital H value. So we can write the base 16 or we can write the base H. Both are same thing. This both H. So both are same thing. Now suppose 678 is here, and now we will divide it by 16 obviously, because the number system in which we want to convert is having the base 16. So 16 dividing the 678, we are getting the quotient as 42 and the remainder is 6. Then again 42 is replacing the 678, and now we are again dividing it by the 16. Now we are getting the 2 as a quotient, and 15 15 here as, sorry, so now we are, when we are dividing 42 by 16, so we are getting the 2 as a quotient and 10 as remainder. And you know, I have already told you in this video lecture, then in hexadecimal system, your 10 is represented by capital A. That is why this capital A is here. Now again 2 will replace the 42 and 2 will get divided by the 16. So for that, obviously we are getting the 0 as the quotient and 2 as the remainder. And then again we will start counting of these remainder values from bottom to up, and now we will try to write them from left to right. 2, capital A, and 6. So dear friend, this is the number in the base 16 which is equivalent to 678 on base 10. So up to this moment, dear friends, we have understood how we can convert a number in the decimal system to any other number system. Means whether it is a octal, whether it is a hexadecimal, or whether it is a binary, or in fact it is a number with any radix r, any radix r. Now we will reverse the problem. Let us say we are having a number in basic radix r. Then the problem is how we can convert a number in radix r to the decimal number. That is why the topic of this time's concern is conversion to decimal number from numbers with radix r. So let us start with the very first example, how we can convert a number given in the binary to the decimal. Again we are taking a very good example for understanding this conversion. Let us say we are having in our hand 1110011 on base 2, and we are trying to learn how we can convert this binary number into the base 10. So dear student, basically these digits in the binary numbers, now they will get multiplied by their positional weights. Basically every digit in the binary number is having certain weight. So when we start from here, from right and to the going to the left, so this particular digit is having weight to the power 0. It is having the to the power 0, and the next digit is having the weight to the power 1, and moving further it is having the weight to the power 2, to the power 3, to the power 4, to the power 5, to the power 6, to the power 7, and going down up to the end of the number. So similar calculation can be done here. This is the given number. Now the last digit, as I told you, this is 1. So the weight of this particular digit is to the power 7. 1 multiplied by to the power 7 plus. Again the next digit is 1. So 1 multiplied by next weight is to the power 6. Then 1 is multiplied by the to the power 5. Then the next digit of the number is 0. It is multiplied by the next weight, which is due to the power 4. Then 0, it is again multiplied by the weight to the power 3. Then 1, it gets multiplied by the to the power 2. Then 1, it gets multiplied by the to the power 1. And finally the rightmost 0, which is having a weight of to the power 0, so then it's get multiplied. And now we can calculate that to the power 7 is 128, to the power 6 is 64, and going down 0 multiplied by 2 ki power 0, obviously 2 ki power 0 is 1, but when it get multiplied by 0, so it gives you the end result 0. Now friends, we can sum up all these values, and now we can have the 230. This is the required number in base 10 for the given number 111001110 on base 2. So this is how, by using the positional weight, we can convert a given number in binary to the number in decimal system. Now move on to the next slide, which is basically the continuation of the previous slide. So dear friends, in the previous slide we were trying to learn how we can convert a given number in the binary to the decimal system. But that was the example of integer number. Now let us say we are having a number with the fractional value. Let us say 101.101. It is on base 2, and now the problem is how we can convert this particular number into the base 10. So now this problem is a two-dimensional. As I told you in the previous slide that the integer part will be calculated in the similar fashion as we did in the previous calculation, but there will be a difference, but there will be a little bit difference for the fractional part, because the weights are changed for the fractional part. Now let us try to understand how we can convert this particular given task. So 101, so you know that to the power 0, to the power 1 and to the power 2, this one is having the weight of to the power 2. Yes. Next 0 is having the weight of to the power 1. Yes. Next one is having the weight to the power 0. Yes. And then plus. Now the fractional number start. Now here this 1 is, it is having the positional weight to the power minus 1. So this 1 gets multiplied by to the power minus 1. Again this 0, it gets multiplied by the 2 to the power minus 2. And then finally the last digit of the given number, which is the 1, it is gets multiplied by the positional weight of this digit, which is the to the power minus 3. So now friends, we can calculate this number easily. So it is here shown in this particular expression, and then finally we can reach to the desired result by summing up all these values, and which will give you the result of 5.625 on base 10. It means 101.101 on base 2 is equivalent to 5.625 in the decimal number system. Now move on to the next slide, which is showing how we can convert a given number into the octal to the decimal number system. So again we will try to understand this particular conversion with the help of an example. Let us say 331 on base 8, it is the given number, and we are required to convert this particular given number into the decimal number system. So again the approach is same as we applied in the previous example, but in the previous example the source number was on base 2, so the positional weights were in the form of to the power 0, to the power 1, to the power 2 and to the power 3. But here friends, the source number is the octal, which is base 8, so the positional weights are in the form of 8 to the power 0, 8 to the power 1 or 8 to the power 2. So similar approach by applying, so we will get this multiplication here 3, this gets multiplied by the 8 to the power 2, because from when we start from here to 8 to the power 0, 8 to the power 1 and 8 to the power 2. So 3 is multiplied by 8 to the power 2 plus next 3 multiplied by the 8 to the power 1, next positional weight, and the 1 is the last positional weight, 1 gets multiplied by the 8 to the power 0. And now we can compute this particular expression, which is 192 plus 24 plus 1, which is 217 on base 10. It means 331 in the octal number system is equivalent to 217 in the decimal number system. Now moving further, extending this particular conversion from octal to decimal, now let us see, we are having the one other example which include the fractional part also. So 33.56 on base 8. Now how we can convert into the decimal number system? So 3, now it get multiplied by the 8 to the power 1. Next 3, it get multiplied by the 8 to the power 0. Then point. So point, right values to the point. This is 5. So 5 is gets multiplied by the 8 to the power minus 1, because this 5 is after the point. and this 6 it gets multiplied by the 8 to the power minus 2. And now we can calculate this particular expression, which gives you the result 27.71875 in base 10. It means 33.56 in the octal is equivalent to 27.71875 on the base 10. Now moving further in this series of converting the number in base r to the decimal system. So now we are trying to understand the last example, how we can convert the hexadecimal number to the decimal number system. Again we are taking a very good example. Let us say D9 on base 16, and now we are required to compute the equivalent decimal number. Now D9 on base 16, again applying the same approach as we did in the conversion from the binary to decimal or in the conversion from octal to decimal. So we will apply the same approach here. So this D, it gets multiplied by the 16 to the power 1 because the base is 16 here, and the 9 it gets multiplied by the 16 to the power 0. It gives you 208 plus 9, which is equivalent to 217 on base 10. Now further extending the conversion from hexadecimal to decimal, now we take another example, E5.A on base 16. Now we will see this particular example is a bit different from the previous one, which was having only the integer part. Now we are having the integer along with the fractional part. So let us try to understand how we can convert this particular number into the decimal system. So again we will apply the same approach. The E gets multiplied. E means the 14 into the hexadecimal. You can remember. It gets multiplied by the 16 to the power 1, which is the weight of this E, and the 5 it gets multiplied by the 16 to the power 0. Then for the fractional part we will multiply this A. You can remember A is represented with 10, and now 10 is multiplied by the 16 to the power minus 1 because A is after the point here in this number. And now we can compute the final value, which is equivalent to 229.625 on base 10. Now moving further, this is the another conversion. Now we will understand how we can convert the binary number into the octal number system. So friends, for making this conversion, we have to group the binary digits into the groups of 3. As the line is clearly stating that conversion from binary to an octal number requires grouping of the binary digits into the groups of 3. So let us try to work out how this all happens. Let us say we are given with a binary number with the value 110110001 on base 2. And now the objective is to convert this particular number into the equivalent octal number. So as the definition clearly stating that first we have to group the given binary digits into the group of 3. So make sure we will start this grouping from this side, from right to left. We will start from right to left, like that, from right to left. So here 1 0 0 and 0 1 1, and again moving further, then 1 1 0, then 1 1 0, and then finally you can think only 2 digit left because in the grouping of 3 you require the 9, and here 1 2 3 4 5 6 7 8 you are given with 8 binary digits. So in the first group you have make it 0 0 1, that's fine, and then in the second group 1 1 0 1 1 0, that's fine. Then in the third group you are only left with the 1 1. So 1 1. So what you will do here, as I am showing in the slide with the 0 in red mark, means you will add the extra 0 here, because adding extra 0 into the left side of a integer number will not change the value. Let us say I am having the value 1 2, and if I say 0 1 2 in decimal. So then 1 2 or 0 1 2 in decimal, they are same value, they are the same value. So that is why we have appended the extra 0 to make it a complete group without changing the value of the number. So that is how we will group the digits when we are trying to convert from binary to octal. And now friends, we can find the equivalent binary value, equivalent straight binary value. Make sure the octal number, in octal number also we are using the number 001, or in some other number like BCD numbers or axis 3 code number. So they also use the number 01. So, but BCD numbers are different numbers, the gray code numbers are different number. So this particular, when I say binary, so this is called straight binary. This means this is straight binary. So what I mean to say, when you have group into the into group of three digits, then equivalent to this you will write the straight binary equivalent. Straight binary, you will treat it as a straight binary, and by treating it as a straight binary, the weightage of this value is 2 to the power 0 and 2 to the power 1 and 2 to the power 2. It means 001 in the straight binary is equivalent to 1. Similarly, 011, it is 2 to the power 0 multiplied by 1 plus 1 multiplied by 2 to the power 1. So it is the 3. So 3, and then again 011, it is the 3. It means the 331 on the base 8 is equivalent to 110 11001 in base 2. Now further extending this particular conversion from binary to octal, let us take another example which also have the fractional number. So now we are trying to convert 111101.01101 in base 2 to the octal number system. So now again we will apply the similar approach for the integer part. We will group, starting group from the right here, and we will end it here. And now let us see on what it happens. How does it happen? So 101, that's fine, 101. Then you are left with 111, that's fine, 111. Here you are fortunate enough that you are ended with the complete 3-digit group. Now for the fractional part, you will start from here, right to left, and right to left you will move into this direction, and you will start from here from 0 1 1. So 0 1 1. Now moving further, in this particular slide we will try to understand how we can convert binary to hexadecimal. Let us remember, in the previous slide we understood how we can convert a given binary number into the octal. So for converting into hexadecimal a given binary number, we have to make the groups of 4. As the line is stating here, conversion from binary to a hexa number requires grouping the binary digit into groups of 4. And now again we are taking a very good example. Let us say 110111101 on base 2. So again we will try to form the group. So as I told you in the previous example, that for the integer part you will start making group from this to this side, from right to left. And now you can see that 1001, this is the one group here, and again 1011. So you are fortunate enough that you are ended exactly what is the needed number of the digits in a group. And then friends, again as we did in the previous example, you can write the equivalent binary value, straight binary. Straight, you can treat it as a straight binary number, and you can write the equivalent value. So equivalent value is what? 1011. 1011 is the 1 multiplied by 2 to the power 0, 0 multiplied by 2 to the power 1, 1 multiplied by 2 to the power 2, plus 1 multiplied by the 2 to the power 3. So it makes it 1 plus 4 plus 8. So it is 13, and 13 is equivalent to D in the hexadecimal. Obviously 13 is equivalent to D in hexadecimal system. And now we can also calculate the 1001, which is equal to 1 plus 8, because the in the place of to the power 1 it is 0, so it is ultimately 0, to the power 2 again 0, so to the power 0 into 1, which is a 1, and to the power 3, which is 8 multiplied by 1, so 8 plus 1, it is the 9. So we can say that equivalent number in the hexadecimal is D9. So now again further extending the example with the fractional value also, so let us try to understand how we can convert this particular number, which is 00110001.11011 binary in binary to the hexadecimal. So again the procedure is same. So we will start grouping of the integer part from right to left this direction, and so here this 1 0, this is one group 0 1 0 0 1 0 1, and another group is what, this is here 0110, yes it is 0110 here, and then finally we are left with only 10, this is 10, so 10 is here, we are left with it. And you know that to make it the group of fours, because we are trying to convert into the hexadecimal, to make it the group of the 4, so now we will append the 3 digit, and we will append the 3 digit to the left, because we are dealing with the integer part, so to make it the group of required number digit, that is 4. So now friends, it is done for the integer part, and now for the fractional part, as I told you that we will do in the reverse direction from left to right, this direction. So we are having a group of 4 like that. Here this is 1101, this is okay, 1101, that's fine. And now we are left with only 21, so ultimately we require more 2 digits, and 2 digit means the 20, and because we are dealing with the fractional part, so we will append the 20 to the right of the this 21 to make it the group of 4. So now we are ready with further calculation. So now what we can do here, we can start again calculating the equivalent decimal of this particular binary, state binary. So 0101, obviously it is equal to 5, so 5 is here. 0110, it is equal to 6, 6 is here. It is absolutely 0, then 0 comes here. Now for the fractional part, it is the 1 plus 2 0, 1 plus 4 plus 8, it is 13, which is a D in the hexadecimal. And now it is the 1 2, both are 0, then 4, then 8. So 8 plus 4 is equal to 12. 12 is C in case of hexadecimal. So now we can further write 065.DC as equivalent to 65.DC, which is on base 16. So this is how, dear friends, we can convert a given binary number, whether it is a complete integer or whether it is a number with the fractional part. So we can convert into the hexadecimal system. Now moving to the next slide. Now in this particular slide we will try to learn how we can convert a number into the octal, into the binary, and also how we can convert a given hexadecimal number to the binary. So let us start with octal to binary. Let us say we are given with 331 on base 8 and we have to convert into the base 2. So 3318, so as we saw in the reverse of this problem, that there was the binary to octal. So when the number was given as a binary, so we were forming the groups of 3 for converting to the octal. But now, the dear friend, the problem is just reverse. We have to convert the given octal number to the binary. So what we will do, we will write the each digit of the octal number into the group of 3 binary digit. So 3 in octal is equivalent to 011, because 1 plus 2 3, again 3011, and then for 1 we will write 1, but to make it the group of 3 we will write it as a 001. So this makes the group of 3, And then what we will do, here, we will write this number in continuation. In continuation means 100, 100, then 110, then 110, and then finally 1111, and the leftmost zero we can drop out because it does not change the value of the number. So dear friends, this is the equivalent value, which is 1101101 in the binary for the given number 331 on the base 8. Now similarly, we can move for the hexadecimal to binary. Similar approach we will apply here. Let us say we are given with D9 on 16 and we want to convert this number into the binary. So what we will do here, we will write the D on hexadecimal into the equivalent 4 binary digits, and you know that D is equivalent to 1101 in straight binary and 9 is equivalent to 1001 in straight binary, and then we will now continuously write these two number like 1001, 1001 and 1011, 1011, and it is the equivalent number in binary for the given D9 on base 16. Now moving to the next slide. Dear friends, up to this moment we have covered all type of conversion from decimal to binary, binary to decimal, decimal to octal, octal to decimal, binary to hexa, hexa to binary. Now what is left only, it is the octal to hexadecimal or hexadecimal to octal number system. This particular problem can always be achieved through the straight binary system. As I am telling you, the base 2, it is called a straight binary system. For example, any octal number first may be converted to straight binary system and then to the hexadecimal system. So that is how we can achieve octal to hexadecimal conversion, and the similar approach may be used for the hexadecimal to octal conversion. So up to this moment, I think we have covered all type of conversion and we have understood what are the different number systems, why they are being used, when the decimal system, number system were already there, what was the need for the binary system, and then we understood if still there is a binary state binary number system is there, then what is the need arises for the octal and hexadecimal system, and finally we ended up with the all type of conversion means any number given in a radix or can be converted to any number with a desired radix r. So with this, we comes to an end of this particular topic. Thank you so much.